Welcome to The Explainer. Today, we're diving into something truly monumental, the Grand Circuit. We aren't just talking about upgrading a few power lines here. We're talking about the physical, structural rewiring of an entire subcontinent. India is preparing for a massive leap in power transmission, completely shifting away from incremental grid expansion toward a brand new, ultra-high-capacity national architecture. It's an engineering marvel, an economic catalyst, and quite frankly, a massive race against time. So I want you to picture this core physical constraint. How do you power a rapidly growing nation with its exploding energy demands without actually running out of physical room to put the wires? I mean, you can't just pave over the entire country with electrical towers, right? It's the ultimate geographical puzzle, and the sheer tension it creates is driving one of the most ambitious infrastructure projects on the planet right now. Okay, let's dive into this, because to really grasp the solution, we first have to understand the sheer scale of the need. 191,000. That's the staggering number of circuit kilometers of new lines that India urgently requires. Just to put that into perspective for a second, that is enough wire to wrap around the Earth roughly 4.5 times. The country is absolutely hungry for electricity to fuel its growth, and delivering it requires an unprecedented web of connectivity. And the financial commitment backing this up, it's just as breathtaking. The National Electricity Plan has lined up a transmission investment of 9.15 trillion rupees by the year 2032. That's a colossal wave of capital designed specifically to solve this exact grid bottleneck. We are talking about a generation-defining investment cycle that is going to reshape entire industries. But before we get into the money and the tech, we've got to understand the roadblock. Section 1, India's massive power challenge. Look, you can generate all the clean power in the world, but if you literally don't have the space to move it, it's completely useless. And that spatial reality comes down to one crucial term: right-of-way constraints. This is the severe physical limitation of trying to secure enough land to endlessly build traditional parallel power transmission corridors. You've got farms, cities, forests, and private property. Running out of physical space for these massive metal towers is the primary force, forcing India to entirely rethink its grid strategy. They simply cannot just build more of the same. So if you can't build out by taking up more land footprint, the only direction left to go is up in voltage. Section 2, the 1150 kV superhighway. This is the technological leap that changes the whole game. Think about the old standards, the typical 400 kV and 765 kV lines, basically acting like country roads. Now compare that to the future. A single 1150 kV UHVAC line can potentially transfer a staggering 6 to 8 gigawatts of power, depending on the exact setup. That is a monumental amount of electricity squeezing through one single pathway. So why does this actually work? Well, it all comes down to some surprisingly accessible physics. By operating at a significantly higher voltage, you actually reduce the electrical current needed for the exact same power transfer. Lower current means lower copper losses, which just means less energy is wasted as heat along the journey. But most importantly, it means you can transfer substantially larger quantities of electricity without proportionally increasing your right-of-way pressure. It's the ultimate efficiency hack for a crowded map. Now, to be clear, this new superhighway architecture doesn't just rip up and replace the old system. It reinforces it. Existing high-voltage direct current, or HVDC, corridors, like the massive Bhadla-Fatehpur line, will keep moving bulk power over long distances. But this new 1,150 kV AC mesh acts like a muscular skeleton laid right over the top, adding incredible foundational strength and flexibility to the entire national grid. Of course, an engineering shift of this magnitude doesn't just happen in a vacuum. It sends absolute shockwaves through the economy. Section 3. A trillion rupee investment cycle. What's really fascinating here is how industry leaders are reacting in real time. Take Simarpreet Singh, the CEO of Hartech Power. He points out that this could open a sweeping investment cycle across everything, from high-voltage equipment and grid automation to testing and engineering design. This is expert validation that we're not just looking at a construction project. This is the catalyst for an entire high-tech industrial ecosystem. So who exactly are the big winners here? Well, 1,150 kilovolt lines are incredibly high-value, highly technical projects. This translates to huge contract sizes benefiting tower manufacturers, line hardware and long-rod insulator makers, conductor suppliers, and civil contractors. But the absolute largest margin opportunity? That goes to original equipment manufacturers and specialized grid tech companies who possess the rare expertise to actually handle these extreme voltages.
And hey, this boom isn't just happening out in the countryside with these massive superhighways. Draft norms around data center redundancy are about to pull highly dedicated 220 and 400 kV power evacuation packages right into the heart of urban tech hubs like Mumbai and Hyderabad. These data centers literally cannot afford to go dark, meaning premium margin work is absolutely flooding in for engineering, procurement, and construction companies, not to mention suppliers of specialized gas-insulated switchgear. Because the economics fundamentally change at this level, Rohit Vijay from the Center for Social and Economic Progress explains it perfectly. Ultra-high-voltage class transformers, reactors, and switchgear cost several times more per unit than your standard lower-voltage equipment. Because of that massive unit cost, even just a handful of these 1,150 kV projects completely shifts the market landscape and the order mix for these manufacturing companies. It's a highly lucrative pivot.
But look, having a cutting-edge blueprint on paper is just the start. Section 4, the real test, execution. Let's face the reality check, right? Because actually building this massive grid means overcoming 3 major sequential roadblocks. First up, strict technical validation, proving the physics works safely out in the real world. Second, domestic manufacturing readiness. Can local factories actually produce these massive specialized components at scale? And third, regulatory approval, navigating a crazy bureaucratic maze to get these unprecedented structures greenlit. And when we say technical validation, we are talking about mind-boggling physical scale and complexity. Engineers have to reevaluate and validate the corridor width, the massive height of the towers, the exact insulation design required to keep that power from jumping, the long rod insulators, the breakers, the giant transformers, and the reactive compensation systems. Every single piece of hardware has to be engineered for absolute extremes. So why go through all this trouble? Why push the boundaries of physics and economics and manufacturing to their absolute limits? Section 5, wiring a renewable future. The ultimate national goal here isn't just about turning on more lights, it's about fundamentally changing where that light comes from. India is deeply committed to high renewable energy integration. But, solar farms in the desert and wind farms on the coast are kind of useless if that green power can't reach the major cities. Today, interregional transmission capacity sits at 119 gigawatts, but by 2032, to make this renewable dream a reality, that capacity has to jump to 168 gigawatts. This upgraded capacity is the literal bridge to a clean energy economy. It completely reframes how we look at the future of our planet. We spend so much time talking about battery tech and wind turbines and solar panel efficiency. But I'll leave you with this to ponder. Is the green energy transition won or lost, not just in the shiny solar panels, but in the unglamorous, ultra-high voltage wires that connect them? Without the grand circuit, the power stays trapped. Thanks for joining me on this explainer. I really hope this sparks some new connections for you.